Okay. Good morning, everyone. I want to welcome you to this month's Microscopy Mondays seminar series that is sponsored by the Centers of Excellence in Hematology. Today, we're going to hear from Joerg Bewersdorf, and thank you again for presenting. I'm going to take 1 minute to take you to our website to just show you a couple of things. So let me get there for that. And this is our website. Hopefully you can see it. If you go to the website, which is CCEH.io, you can find the homepage here where you'll actually, right here, you can see the Microscope Monday schedule. If I click on that link, it shows our speaker today. Below that link, you'll be able to find actually the recordings of previous talks by our speakers in this seminar series, in case you wanted to hear something again or you didn't get a chance to hear it before. And those are very simple. You just click on the link right here. They'll load up and you hit the arrow button to start the recordings playing. So that's one thing I wanted to show you. The second thing I wanted to show you is if you click on the services link, what you will find is different services that these centers of excellence have, different cores that they provide. And for example, in today, how do I evaluate and analyze cells or pathways? If you click that link, you might find here cell analysis. And if you go through there, you can see different cores, including metabolomics, metal, flow cytometry. A couple of ones I wanted to point out to you, for example, is the intravital and 2D, 3D microscopy offered at the Indiana Center of Excellence in Hematology. And down here, if you keep going on, morphologic analysis at Yale, which is imaging cores at Yale that can help you with your research, and several others as you go along. So if you click on this services site, you can find all of those kinds of things. And one final thing is if you click on the funding link here, what you will find are currently sponsored individuals and some projects. But if you just scroll down this page, you'll learn more about our P&F program, which has type A and type B grants. The type B grants are for $75,000. They're currently closed. We just had a cycle go through, and those proposals are under, have just been awarded. But type A proposals are essentially open year-round. You can apply for them anytime. And what they really are is credits for using a core that's sponsored by the Centers of Excellence, and that can be up to $12,000. They're really like a one-page application where you bank credit money at a different core for some of your research. And the applications will be accepted on a rolling basis. And they're really suited for trainees who want to master a new technique or acquire new skills to enhance their competitiveness. And I highly recommend you go to this site. You can look at them. If you want to know about a few that have been sponsored so far, you can scroll down here and see the different individuals who received P&F funding and who they are. So if you're interested in applying for that, go to this website, which looks like this. So I will stop sharing for now. And then I just want to introduce Dr. Bewersdorf. He comes to us from Germany, but he's actually now at Yale. He got his degree in physics and then in physical chemistry, and has been at Yale since 2009, where he is a professor in the Department of Cell Biology, Biomedical Engineering, and Physics. I don't know if that's a whole department or if that's 3 departments, but we're really excited to hear from you again this month, Joerg, and thank you for offering to do this, and we'll turn the time over to you to share your screen.
Thank you. Thanks, Diane. And yes, it is 3 different departments.
Okay, I thought that was probably true. I couldn't. I couldn't figure out how they would exactly be together, but I didn't want to say that.
So, okay, I'll share my screen and then I start my presentation, and then I need to probably flip my display. Okay, so you should see my presentation screen now.
We do.
Okay. So today I want to introduce you to the basics of confocal microscopy here at this lecture. And I will cover the fundamentals here. What is a confocal laser scanning microscope? Why do we use it? Then how does it actually work? And then I'll talk a little bit about variants of these scanning microscopes, for example, the spinning disk microscope. And then I end my talk, which is probably the last 30% or so, with more practical tips. So which imaging parameters do you find on your confocal microscope? And you can tune these imaging parameters, and it matters a lot how you tune them. So I try to explain a little bit what these imaging parameters actually mean and what you want to optimize them for. And I'll end my presentation today with a few best practices, which is essentially a little bit of a laundry list of things that I want to share, which is by no means complete. And I'm sure other people in the audience like Ken have their own best practices to share, and I would be happy to have a discussion after my presentation here. I'm perfectly fine if you interrupt me with any questions. I am probably not able to see any typed comments in the chat because I'm too distracted with the presentation, but just shout out if you have a question, or Diane maybe can have a look for that as well. Otherwise, we can discuss it afterwards. I also have plenty of time after the presentation. If you want to hang on, we can talk for another hour or so. So now starting my actual lecture. So what you see here is the motivation for confocal microscopy. This is a thick sample, a 3D culture of memory epithelial cells here imaged not with a confocal microscope, but with a normal wide field microscope. So a camera-based system with a lamp illumination or an LED illumination. And this is a 3D stack where we look at the different sections of that 3D stack here in this movie. And you see on one hand, nicely here the nucleus and the individual cells, but you also see a lot of haze. You see all this background light from the cells above or below the plane you're looking at. And that is preventing you from a kind of a detailed quantitative analysis of subcellular details here in this particular sample. So this highlights here the problems that a wide field microscope has, namely that it's very bad at excluding out of focus light from your image. And the confocal microscope is solving this problem. So I'll explain in the next 10 minutes or so how the confocal microscope does this. But to do that, I want to remind you briefly here of the concept of the point split function. If you are not familiar with it, it is the image that you get if you image a single point object. Think of it as a very small fluorescent bead or fluorescent particle, or even a single fluorescent molecule like a GFP molecule. It will not appear as a single point on your detector, but it will appear as a blurry object, like, for example, an airy pattern. I spoke about the basics of microscopy about 2 months ago, and if you're interested in more details there, I encourage you to go back to the recording of that presentation. But for now, suffice to say that it's just that the point split function describes the imaging properties of your sample by describing how a single point object looks like. And then you can think of your sample consisting of many of these single point objects, and the point split functions add up to form your final image. So how does now the point split function in 3D of a wide field microscope look like, not the confocal microscope? And how does that affect your image so that you get all this out of focus light? So for that, I'm created here a simulation of a 3-dimensional test object. Okay, it consists of these little disks in the focal plane. So they're just on the cover slip surface, if you like. So this is the side view of these discs. And then there's one tiny little disc a little bit further into the sample above that plane of these discs here. So, and this would be now the Poinsot function with which we image that sample. And that Poinsot function looks quite well behaved. Yes, it is a little bit blurry, as any Poinsot function of a diffraction limited microscope is. But it is good enough to resolve these individual discs in the focal plane. And even in the depth direction, while it is worse in size, it's about 2 to 3 times bigger, it seems to be quite limited in its extension. However, if we plot this Poinsot function here on a logarithmic scale, then you see that this color table is deceiving a little bit. There is actually signal above and below your Poinsot function here. It's just quite weak and therefore hard to see. And it makes total sense that there's light above and below the Poinsot function, because if you think about it, these are waves of light or particles of photons, light particles, going through here, through the focus, and then going out on the other side. And if they are in the middle in the focus, they also must be above and below since they traveled all the way. So the energy here of the light coming from the top in a defocused manner, being focused into the Poinsot function and being defocused again on the other side needs to be preserved. So we have conservation of energy here. And therefore, there must be light above and below that Poinsot function. So, but you can still argue, well, it's not that much. So what's the big deal? Well, the problem is that while it's not a lot above here, it covers a large area. And this large area will illuminate a lot of different objects. So now you get a little light from many, many objects. And that adds up to a lot of background. So let's simulate this. Okay, so this is this image here, now imaged with this Poinsot function, and everything looks fine. However, if you go out of focus, okay, now we image here planes, not in the focal plane, but slightly above and further above. You see that the signal doesn't disappear. It doesn't become black. It becomes this medium level intensity level. And that is exactly for that reason I described. So up here, while each of these disks is illuminated only a little bit, or many of them emit light at the same time and contribute to the signal here in each pixel. So the wide field microscope really is terrible in excluding out of focus light from objects out of focus. And in this case particularly, right, we have this tiny little object here. It's barely visible here in front of that background of all the other disks here. So we'll look in a few minutes at the same simulation with a confocal microscope again. I'll show you the comparison there. But first, let me explain now what the confocal microscope is and how it solves that problem. So the confocal laser scanning microscope is, first of all, a laser scanning microscope. What's a laser scanning microscope? A laser scanning microscope is a microscope where you have a laser beam that you focus into your sample. And then you excite fluorescence here in this laser focus. And the fluorescence is collected again by the objective and projected onto a detector. And that detector will just measure how much red fluorescence light, for example, in this case, reaches the detector. It then plots that signal that it measured on the screen as a single pixel. And now we scan that laser focus across the sample. And we can move it here. We can do it by moving the sample across the laser focus. That's easier for me to animate here. Or in practice, we move the laser focus across the sample rather than the sample across the focus. But it gets the same result, so that you, over time, image one area of the sample after another. And the detector will detect that signal sequentially, and it will be represented as one pixel after another on the screen. And now we have scanned a line, And then we can scan the next line and the next line and the next line, get a two-dimensional image, and we can also move the sample or the laser focus in the third dimension and get a three-dimensional image that way. So does this solve that problem that we had with a wide field microscope of the depth discrimination problem? It doesn't, right? And the reason is that the laser focus is brightest here in the center, but again, there's also photons in front and behind that laser focus where we still illuminate fluorescence, and that fluorescence will still be detected here by our detector and creates the same background effect that I showed you in the previous slide. So just going from a wide field illumination to a laser scanning illumination does not solve the background problem. So now what comes in is the fourth word here of the confocal laser scanning microscope, confocal. So we do a small modification now to this laser scanning microscope in form of a pinhole in front of the detector. And we focus the light from the focal plane here right into the middle of that pinhole and measure the light then coming through the pinhole with the detector behind it. So why does that make a difference? So let's look at what the light travels here. So the laser light will be focused into the focal plane, and we get kind of this Poincare function of the laser focus here in the sample, right? It's brightest in the center of the focal plane, but there's still some light contributions in front and behind the focal plane. And now fluorescence being emitted from the center of that laser focus will go right through the pinhole and be detected in a very high efficiency. Light, however, that was emitted from a plane behind will be focused in front of the pinhole, will be defocused in the pinhole itself, and only a small fraction of this light will now be able to pass through the pinhole. And the same is true for light being emitted from a plane in front of the focal plane. It's not focused yet when it reaches the pinhole, and therefore, again, only a small fraction of this light will go through the pinhole. So we can now plot the probability of light being emitted from a particular area in the sample of that probability of going through the pinhole. So the probability of going through a pinhole when it comes right here from the focal center is high, but when the light is emitted from any other area around the focal center, then the probability of detecting fluorescence is low because the pinhole will block it. So now you have a certain probability of exciting a molecule, a fluorescent molecule, that's given by the laser focus, right? And then we have a certain probability of detecting light that was emitted from these excited molecules. If you combine these two probabilities, first exciting a molecule and then detecting the light from that molecule, then we get our effective Poincare function of the confocal microscope. And what we do for that, we multiply these two functions. So in the middle, you have 100% and 100%, and you get 100% here. But if you are somewhere out here, you have 10%, let's say, you have 10% here. 10% times 10% is 1%. So you now suppress all these out of focus distributions quite effectively by having added this pinhole in your beam path. So it's this pinhole in the confocal laser scanning microscope that is creating that background suppression effect. So let's come back to the earlier simulation that I showed of that wide field microscope. And let's do the same simulation now with our confocal Poincare function. If we, on this logarithmic color scale, you can now see that the background is suppressed much, much better than it was in the wide field microscope. And if you now simulate this image of this test object with this confocal microscope, you now see that the background has disappeared, right? So in the focal plane, the difference is not very big. You kind of see the same thing. But when you move out of the plane, suddenly the light disappears. And while this is weak here, it stands clearly apart here. You can see it here a little bit better. This extra object here stands clearly apart from the background now. It was much harder to detect with a wide field microscope. So while here the average signal did not change in each plane. So if you integrate the signal that you get in each of these images would always be the same. Here it does. The out of focus signal is strongly reduced, and that gives us this, this superior 3D imaging capabilities of the confocal microscope. So now let's come back to that original sample that I showed you of that this 3D culture sample. And that's actually not a sample by myself. That was provided by here James Jonkman, who is working in Toronto, and who I could convince to share these slides with me. So here now we see on the left, you see that wide field image, and on the right you see another image taken with a confocal microscope, not exactly the same 3D culture, but same staining from the same sample here. And now I think you see a clear difference in the out of focus suppression that you get with the confocal. So this is the motivation why you want to use a confocal microscope in your research. Anytime you image samples which are thicker than a few microns, if you really want to look at small details, subtle details, the confocal microscope is a good choice there. So I'll show, now let's get more into the technicalities, and I'll show one slide first that I already showed 2 months ago, and that is what's the resolution that we can achieve here. And this is essentially the same equation that I showed 2 months ago. In the focal plane, so in the XY direction, you get a resolution which is proportional to the wavelength of light divided by the numerical aperture of your objective times 2. Okay, so 1/2 times lambda over the numerical aperture. The numerical aperture is a property of your objective lens, and you will see it printed on your objective lens. Axial resolution is about 2 times the wavelength divided by the numerical aperture squared. So the numerical aperture has a very strong effect on your axial resolution in particular. If you go from a 0.7 numerical aperture to a 1.4 numerical aperture, you will double your XY resolution and you will quadruple your axial resolution. So you get a much better depth discrimination there. So if you need good depth discrimination, where you really want to see features which are just a micron apart in the axial direction, then choose an objective with a high numerical aperture. So now let's look into a confocal microscope. So how does it look like on the inside, and how do all these technical components allow us to do what we like to do?
Hey, Joerg,
yes.
Can I interrupt for a second? Will you go back one slide? It's a question from me.
Yeah.
So if the numerical aperture number really helps improve this depth, why does anybody use anything with a lower numerical aperture?
Well, there are 2 possible reasons. One is by choice, and the other one is not by choice. So sometimes you want to do very rapid imaging. Let's say you have cultured cells on a cover slip. You just want to see how many there are, if they divide, these kind of things. In that case, you just want to take 2D images, not 3D images. And you actually have no interest in seeing only a part of the cell. You want to see the whole cell. So you don't want to filter out any light from a micron or above or a micron below. So in that case, you want to see the projection of the whole cell, and going to a smaller numerical aperture allows you to do that. Let's say if you put in values here, 500 nanometers times 2 is 1000 nanometers, so 1 micron divided by, let's say, the numerical aperture of 0.5 squared. So divided by 0.25, so that's times 4, that gives you a 4 micron axial resolution, and that covers essentially the thickness, let's say, of HeLa cells or cells growing on cover slip, and then you can capture the whole cell in a single 2D image. That would be by choice. The other reason why you go to a numerical aperture is if you want to get a very large field of view. For a larger field of view, you need to go down with a magnification of the objective. You can't work with a 100x objective. You might need to work with a 20x or 10x objective. And the manufacturers are simply not able to produce these low magnification objectives, which have a large field of view, to create them with a high numerical aperture. So you need to compromise on the numerical aperture if you want that large field of view. And that's why you often end up not working with a high numerical aperture.
Good. Thank you very much.
Sure. So now let's have a look into the confocal microscope. Or at first on the outside. The confocal microscope consists generally of, I would say, 4 different elements. You have a microscope stand, microscope body with eyepieces, essentially identical to what you get on the wide field microscope. In fact, it is a normal standard wide field microscope. Attached to it, you have a scan head, and we'll have a closer look into the scan head in a minute. That's where all the fancy optics of the confocal microscope is, including the pinhole, etc. The confocal microscope is a digital microscope, so it will be run with a computer, and the images will be displayed on the computer screen. And then you have all kinds of external electronics, which doesn't fit into the scan head, where the lasers sit, some power supplies, additional computers, all that. And that's usually hidden away in some additional box sitting next to your microscope. So now let's have a closer look. Talk about a few technical details here, and then we have a closer look into the scanner itself. So the 2 most important elements of a laser scanning microscope are the detectors and the light sources. So the detectors, there are 2 kinds. The commonly used one in a single beam laser scanning microscope, and we'll come to what I mean by that in a few minutes, are photomultiplier tubes. So these are in a way fairly old-fashioned devices which are still in operation, where you have a photocathode which will transfer photons into electrons. These electrons are then accelerated in a high voltage electrical field. These highly accelerated electrons then hit these diodes, where they will release more low energy electrons. These electrons will then be accelerated again in an electric field, hit another diode where they create more electrons, etc., etc. You get this whole avalanche effect of electrons, which in the end you detect as an electrical current by your anode. And that way you have translated your light into an electrically measurable signal now. So this electric current is what then the microscope is digitizing and displaying as your pixel intensity or the signal on your computer screen. So the second kind of detector that we use in these microscopes are cameras. And this is in particular used in the spinning disk microscope. And of course, it's also used in the regular wide field microscope. A camera consists of an area of pixels, for example, 512 by 512 pixels, or the new cameras have 2000 by 2000 pixels or so. And here the photons that hit each pixel are absorbed and produce an electrical charge. That charge is then accumulated over the acquisition time of that camera. So let's say 50 milliseconds or a second. And then the charge that has been accumulated in each pixel is read out and again translated into a digital signal that is displayed on the computer screen as your image. So there are 2 different kinds of cameras. There is the CCD camera. That is the camera that traditionally has produced the highest quality images until about 8 to 10 years ago, where it has been replaced by the scientific CMOS cameras. And all modern cameras, all modern microscopes, any microscope which is younger than, let's say, 5 years or so, maybe 10 years, is now using these scientific or SCMOS cameras. These are very closely related to the cameras that you have in your cell phone camera. They are essentially the big brother, the higher quality version of these cameras. So that's on the detector side. And then as a light source, we use a laser. Lasers have the advantage over conventional light sources like halogen lamps or LEDs. They have the advantage that they are monochromatic. That means they only emit one wavelength at a time. They have low divergence. That means all the laser light is coming out in one direction, which makes it easier to efficiently steer it towards the objective and focus it. And they are a point source. So that means we can, if we focus them by the objective, they will produce the smallest possible focus, namely a diffraction limited focus. And that will determine the resolution of our laser scanning microscope. So this is just showing here some of the principal components of a laser. I'm not going into depth here. What I want to point out is that you can use different kinds of active laser media, that the pump energy can come from different sources, etc. And that just means there's a number of different laser technologies out there, especially in older microscopes. For example, you find gas lasers still. But nowadays, in the modern microscopes, they essentially all have been replaced by solid-state lasers, like laser diodes or fiber lasers, which are smaller, much more robust, and much more long-lasting in your microscope, and much less need much less service. Okay, so that was what I want to say about detectors and light sources. And now let's have a look into our confocal scan head. So this is taken from a Leica microscope, but the confocal microscopes by other manufacturers look fairly similar to this one. And I think you will find in general the same kind of devices there, or alternative solutions which yield you similar results. So here is a description of all the little numbers in there. I'll leave that for you to look at later if you're interested in from the recording. But we will now zoom in here a little bit more, and I'll guide you through how the light is traveling through this scan head. So just to give you an orientation, the microscope body with the objective is sitting here below. The scan head is mounted on top of that wide field microscope stand here in this particular drawing. Only the scan head itself is shown, and then the objective is shown, and the sample is shown here of your normal wide field microscope. So here's our visible laser light source. They are alternative light sources, but we're not talking about those. And light is now coming out of that laser. The first thing it will experience is some kind of adjustable filter, which is typically an acousto-optical tunable filter, which allows you to tune the intensity of that laser beam. And it also will turn off the laser beam when it's not needed. And it can do so in a very rapid manner, pixel by pixel, essentially. After it passes this AOTF, it will hit an excitation beam splitter, which couples the laser light into the common beam path of the fluorescence beam. In this particular case, this is also an electronic version of a beam splitter, but this could also be a piece of glass which reflects the laser wavelength and transmits the fluorescence wavelength. The light is then traveling through here until it reaches these scan mirrors. From the scan mirrors, the light is then traveling further into the objective, and then it's focused here into the sample. So the scan mirrors are an essential component here of a laser scanning microscope, since they will allow you to not just produce a stationary focus in the sample, but to move that focus across your sample. So the scanners will tilt. That will move the beam, and it will shift the focus here in the across your sample. And then you tilt it in the other direction, and then the focus is scanning in the other direction. So by tilting the mirrors back and forth, you will be able to move the focus back and forth across the sample. And you can do that in a very rapid manner, like 1,000 times a second without a problem. So what happened here? Oh, I think I accidentally pressed the wrong button. Okay, so now we are. So let me go back here, show you that animation again. So by tilting that scanner here, we move the beam across the sample back and forth. So now at a particular point in time, we will hit some fluorescent molecules here with our laser focus in the sample. And from there, fluorescence light will now emerge, right? So the fluorescence light is now collected by the same objective, and it's directed back to the scan mirrors. these scan mirrors will now undo the scan motion that they introduced on the way in for the laser light, right? So the fluorescence will be emitted from the same spot the laser light was projected to. So the fluorescence will travel back on exactly the same path that the fluorescence traveled, that the laser light traveled. And now you hit the scan mirrors on the way back, which are still in that tilted orientation, which they were tilted to get the laser focus into that spot in the first place. And they will now undo that tilt motion for the fluorescence. So the fluorescence will now be stationary. The fluorescence beam will now be stationary when it exits the scan mirrors here. And it will now hit that main beam splitter here, which we use to couple in the laser light. It will pass through that beam splitter, and it will hit our pinhole. You saw the pinhole in that simplified animation I had at the beginning of my talk. And that pinhole will now filter out any out of focus light that was emitted from planes above or below the focal plane. So now the fluorescence is cleaned from the fluorescence, from the excitation light, and it's cleaned from the out of focus contributions. And now it's going into our detector unit. And here we use, for example, in this particular setting, prisms to spread the different colors spatially, and then these individual colors can be separately be directed to different detectors so that we can take multicolor images simultaneously, right? So in this case, we would this would be red fluorescence. That red fluorescence would be here traveling the red part of that rainbow spectrum and would end up at the photomultiplier, which is adjusted to detect the red fluorescence. So, and then of course the fluorescence light is detected here, that detector. So that's essentially what I wanted to show you about the technology inside a regular confocal laser scanning microscope. So next, I want to briefly talk about variants of these confocal microscopes or scanning microscopes. So what we talked about so far is the so-called single point scanning confocal microscope. You have a single laser focus, which you project into your sample and which you then move across your sample rapidly, and thereby you cover the whole sample. But there are other ways how you can scan your sample with structured light, essentially. You can use, instead of one focus, you can use multiple foci, or you use a line profile and scan the line just across once. Instead of scanning in 2 dimensions, you only now need to scan in 1 dimension. Or you can use multiple lines to scan the sample, or you can use completely random patterns of foci, if you like, and thereby cover your sample. All these methods exist in commercial systems. I'll focus on the first 3 here. And the first one we already discussed, right? That's what we colloquially call the confocal microscope, and the size LSM 780 or 880 with the area scan is one of these systems, or the Leica SB8 or Stellaris, Olympus, Nikon, they all have these single point scanning confocals. The multi-point systems are typically these spinning discs microscopes or Nipkow disc microscope, and you might have heard the term Yokogawa. Olympus offers it, and Endor now has this Dragonfly confocal microscope. Line scanning systems are a little bit rare, more rare, but Bruker, for example, has this Optera microscope. Zeiss used to have a 5 Live system, and there are probably a few others. And then there's also the Zeiss Apotome, the OptiGrid, Zeiss Vivatome, which are covering these stripe patterns or random patterns here. So each of these technologies has different advantages and disadvantages. So the single point scanner is most flexible. It has the highest resolution, and it's best in suppressing this out of focus fluorescence. However, it's relatively slow since you have only one focus with which you have to scan the whole sample. And it requires fairly high intensities in this focus to produce enough light in a short time so that it doesn't take ages to image your sample. So the spinning disk microscope in comparison is much faster because now you have, let's say, 100 or 1,000 foci scanning the sample in parallel. So So you can be done in fractions of a second with your image recording. However, you lose the flexibility of these systems where you can, for example, easily switch between 3 and 4 and 5 detectors, adjust the color range, adjust the zoom, what you see. You lose that flexibility with a spinning disk. The single line scanning systems are similarly fast as the spinning disk microscopes, and they're similarly limited in their flexibility. So I would say these two technologies compete against each other a little bit. And then these other systems primarily have advantages because they are, I think, a little bit cheaper, because they can work instead of with lasers, with lamp illumination. But they require some image processing to get kind of a good image quality out of it. So I want to briefly talk about here this multi-point and the single line scanning system to show you how these systems look like. So the spinning disk confocal microscope actually has a fairly simple setup. We have our objective down here and our sample down here. And then we have a microlens disk, which is linked to a pinhole disk, and they can rotate synchronously with each other. So the microlenses are illuminated, or let's say 100 or so microlenses are illuminated by the laser illumination at a particular point in time. Each of these microlenses produces a little focus, which is aligned with the pinhole of that pinhole disk. So the laser light will pass through these pinholes, and now the pinhole pattern is projected into our sample, where it will now create excitation of our cellular sample, depending on how much fluorescent molecules are in each focus. So the fluorescence is then collected by the objective and focused back onto the pinholes again. That's the same idea as with the single beam confocal I mentioned before. The pinholes are used to filter out any out of focus blurriness that we get from the out of focus excitation. And now we project the pinhole pattern onto our camera. We have again a beam splitter which separates the fluorescence and the excitation light here, and that allows us to separate the two. And we now create that focal pattern here on our camera again. And we can see now the fluorescence in each of these foci. And now we rotate that disk very quickly, and the pinholes and microlenses are arranged in such a pattern that by rotating the disk, these points will cover the whole sample uniformly. And you wait with your camera readout, so you accumulate now the fluorescence from that whole scan on the camera, and then you read out the camera image, and you have now a confocal image recorded with your camera. So that's how the spinning disk microscope works. And then just very briefly here about that line or slit scanning confocal microscope. Instead of projecting a laser focus into the sample, we project a line into the sample. We then project that line, the fluorescence from that line, onto a slit instead of a round pinhole, like now a slit-shaped pinhole, and again remove out of focus fluorescence, and then we scan that line now with a one-dimensional scanner. We don't need to scan in 2 dimensions across the sample back and forth, and we can either use a regular camera to detect our fluorescence and scan that line profile across the camera as we do with a spinning disk microscope, or we use a slit-shaped, like a line detection camera, which only consists of line. Okay, so that's enough about kind of the underlying optics technology here. I want to spend now the remainder of my time talking about the parameters that you as a user can control on your confocal microscope, and where you actually have power over, and where you can also mess up your recording if you don't understand what you're adjusting here. So bear with me, please. This is a little bit of a list here we have to go through, but I hope that by having the recording of this talk, you can look back at the recording later and can find these details again when you're sitting in front of your confocal laser scanning microscope. So the first group of parameters I want to talk about are these first three factors. So you as a user have control over at least two of these three. You can determine the zoom factor, which determines the size of the scanned field of view you are looking at, and that you use to adjust the field of view. And you can also tell the microscope how many pixels you want to have in that field of view that you're imaging. So in how many pixels do you divide that field of view? And you can go, if you want to image more quickly, you choose less pixels. If you want to have more details in your image, you would choose more pixels. And then there's the pixel size, which is related to these other three, namely that the field of view is equal to the number of pixels times the size of each pixel. So by changing two of these factors, you will determine the third one. So as a user, you typically select the field of view. So you tell the microscope, for example, I want to image 100 by 100 microns or a zoom 2 or something like that on your microscope. And you want to have 1,000 by 1,000 pixels. So now if you have 100 microns divided by 1,000 pixels, that means every pixel will be now 100 nanometers big. So to illustrate this, I've plotted this here. So here you see kind of a matrix of 4 different scenarios. In the different rows, you see the different zoom factors. So here we have a small zoom factor, which means we image we zoom in less, we image a larger field of view. So let's say this field of view, here see a larger zoom factor, we zoom in more, we image a smaller field of view, and then you can split that field of view that you selected now into, let's say, 1024 times 1024 pixels, which means each pixel will be fairly small. Or you can split that same field of view, let's say, in a smaller pixel number, for example, 256 by 256 pixels. And you see now that results also in the pixels then becoming bigger. And you see you'll be able to see less details there. So the pixel size in the end matters. If you go back to the lecture 2 months ago, because the pixel size should be selected to fit to the Nyquist criterion, so that you are not losing resolution by choosing too large pixels, for example. So the second group of techniques relate to how fast you are able to take an image. So you can typically select the scan speed on these microscopes, and that means that you select how many lines are scanned per second. The typical value would be 400 hertz or 400 lines per second or 1,000 lines per second. And if you go to a higher value, that means you are faster in your acquisition. If you go to a lower value, then of course it takes longer, but you'll also have more time to accumulate fluorescence, so you get a higher quality image. You can also typically select line averages and frame averages. That means how many lines are summed up to form the line that is then displayed in your image, or how many frames are added up before the microscope says that image is finished acquiring. So the more averages you choose, the better your signal will be, but also the slower the microscope will be. If you choose 4 averages, then of course it will take 4 times longer than if you just scan once. And then some microscopes allow you to choose between a uni and a bidirectional scan. And I'll show what I mean by that in the next slide. But first, here I want to show how these parameters all will impact how long it will take you to take a single 2D image. So the frame acquisition time is equal to the number of lines that you chose to scan. So that's based on the pixel size. So let's say if it's a 1024 by 1024 image, you need to scan 1024 lines, right? So you have, let's say, 1024 lines times how often you average each line. So if you have 4 times average, that will be 4 times more. And then how often you average each frame before you say the imaging is done. And then you divide that number by the scan speed. So how quickly can the microscope scan these lines? So, for example, if you say that to 1,000 lines per second and you have 1024 pixels, without any line averages, it will take you about a second to finish that. And if you choose the bidirectional scan, this will be divided by 2 because it will be twice faster. And that's generally your frame acquisition time. And then there's a little bit of a kind of, if you want to look really carefully, there's a little bit of overhead. It will take a little bit of additional time for the scanner to move back to the start position, for example, and start a new scan, which you technically need to add to this acquisition time as well. But from this, you can average, or you can estimate how long it will take you to take a single image. And you see that these parameters all linearly go into this frame acquisition time. So by changing them, you'll change your frame acquisition time quite significantly. So I want to come back briefly to what is line averages and frame averages. And then I want to show you what the difference between uni and bidirectional is. So this is frame averaging here. So in frame averaging, you will scan one line, then you scan the next line, then you scan the next line until you scan the whole image, okay? If you chose 1000 Hertz scan speed, it will take you a millisecond to scan the first line, 2 milliseconds for the second line, 3 milliseconds. After 1000 milliseconds, you have scanned that whole image. Now, let's say you chose 4 times frame averaging. You repeat that whole process, or the microscope repeats the whole process for you. It scans again, first line, second line, third line, etc., until it finishes a second whole scan of that frame. It will then do a third scan, and it will then do a fourth scan. And after about 4000 milliseconds, you will be done with your 4 times frame averaged image. And this is a little bit simplified because I neglected this overhead I was mentioning a minute ago. If you do 4 times line averaging, you end up with the same image with the same signal, but you accumulated it in a different fashion. So here you image one line, then you image the same line again, the same line again, and the same line again. So now you have, after 4 milliseconds now, you are done with that first line. You then repeat the same process for the second line. After 8 milliseconds, you're done with that. The third line, fourth line, etc. And again, after about 4 seconds, you're done with the acquisition of this 4 times line averaged frame now. So why do you choose one over the other? The advantage I see with the line averaging is that you get less motion artifacts, because anything which was in the top part of your frame, for example, after a few milliseconds, you're done imaging that part. You're not revisiting that area of the frame again with the next frame average. So you will not get a motion blur if your object moved over the frame over the time it took to acquire the whole frame, right? So which might have taken 4 seconds. That might be a motion of a live sample, but it can also be drift. So if your stage drifts slowly, by using line averaging, you'll get less artifacts than when you use frame averaging. So I'm personally a fan of using line averages over frame averages. So then let's come to the unidirectional versus the bidirectional scanning. Unidirectional is essentially what I've showed you on the last 2 slides. You scan a line, you move your scanner back, you scan the second line, and you turn off your laser on the way back. So it's the laser is only on the forward scan, but on the backward scan where you move your mirror, the mirror needs to tilt back to the original position to scan the second line, right? During that time, you turn your laser off. But that means you're actually imaging your sample only at 50% of the time. 50% the laser will be on, 50% it will be off, namely on the back scan. Oops. In the bidirectional scanning mode, you will actually leave the laser on the back scan, and you use that back scan to scan the next line. So you forward scan first line, backward scan second line, forward scan third line. This is twice as fast as the unidirectional scanning, and it seems like a no-brainer that everyone should do it. However, it's electronically not that easy for the microscope manufacturers to implement it, because it not only has to work for one particular scan speed, but it has to work for all scan speeds the microscope offers, and it has to work for all zoom levels the microscope offers, which will each change the mirror motion that the scan mirror is experiencing. So because of this electronic fine-tuning that's required, because keep in mind that these lines need to be perfectly aligned with each other so that you don't get weird stripe artifacts here. This is not necessarily the default mode the microscopes operate in. But the newest microscopes, from my experience, work really reliably in this bidirectional scan mode, and something which you definitely should explore if you're impatient or you don't have that much time to acquire images. So then the last group here of these parameters are the z-steps, the number of z-steps and the z-step size. That's what you adjust if you want to take a 3D data set, right? You need to, that determines the size and also the pixel size or the voxel size in a third dimension that, by choosing these values. So then there's a second group of parameters that you can adjust. You can adjust the pinhole size. A smaller pinhole means that pinhole effect will become stronger. You get better zero resolution, but you also lose now a lot of fluorescence. So if you have really weak signals, you might actually want to open your pinhole. You get more signal at the expense of worse axial resolution. We talked about the photomultipliers with their diodes and the voltages, which will accelerate electrons. You can adjust this voltage with a photomultiplier tube gain. And the higher you go with the voltage, the more the electrons will be amplified and the higher the current will be that you measure. So you need to adjust this PMT gain to get the maximum contrast in your image. Some microscopes also offer that you can adjust the offset of that photomultiplier tube, the offset voltage. I would recommend do not touch that. Do not adjust this value. It will seemingly reduce background, but you also will get rid of any weak signals in your sample. So it's a very bad practice, since it can lead you or it can lead to weak signals being clipped off, and you will get artifacts or misinterpretation of your images. Then, of course, you can choose which laser wavelength you choose to excite different colored probes, and you can choose the laser power. So how bright should the laser be? And that will influence how much you bleach or how much signal you get from the sample. And you can also choose which detection filters you're choosing, and you should match these to the fluorescent spectra of the dyes or fluorescent probes you're using. And here, the last time, 2 months ago, we talked briefly about bleed through or crosstalk, and that's where these values really matter. And then you can choose the bit depth, and that tells you in how many bins the signal amplitude is divided. By eye, you can only see about 8-bit. That's 256 grayscale levels. But if you want to do a very high quality quantitative analysis of amplitudes, and you have a very large dynamic range of signals, let's say very bright objects in the sample, but also very dim ones, and you want to analyze both of them, you probably want to go to 12-bit or 16-bit image quality. Okay, so then for the very end, I just want to end here with my laundry list of good practices. So first, talking about objectives in the samples. You want to pick a high numerical aperture objective if you want good resolution. If you need a large field of view, that's where the magnification of your objective matters. You don't need to choose a high magnification because you can always zoom in with a confocal microscope. But you want a high numerical aperture if you want good resolution. So high numerical aperture for good resolution, and magnification, low is good if you need large fields of view. But remember that it will come at the cost of a negative impact on your numerical aperture. If you image a little bit deeper in the sample, let's say about 5 microns or so deep in the sample, then you should pick an objective where the refractive index of the immersion medium is matched to the sample. So if it's cells, live cells in a aqueous medium, pick a water immersion objective. Classical advice: make sure that the objective surface and the sample surface is clean especially if you work with immersion medium. Often enough, that's not the case, especially if you use an imaging facility. You never know if the user before you accidentally got oil on the water immersion lens. So make sure that these are clean before you mount them, and leave them clean after you're done imaging. Use number 1.5 cover slips. That's the cover slip thickness. It seems intuitive to use number 1s or number 0s, but all objectives are corrected for number 1.5s. And make sure that your sample lies flat on the sample stage, especially if you have a sticker on it which labels the sample, or nail polish or so, which maybe extends a little bit too much to the outside. Your sample on an inverted microscope in particular might rest on this nail polish or that sticker, and that will tilt the sample slightly, and that will decrease your image quality, and also will make scanning a sample and finding the area of interest hell, because the sample gets out of focus all the time. And then last slide. So with imaging parameters on the confocal microscope, typically the pinhole set to what's called 1 air unit as a default is a good size. There's no need for you to really play with this. The pixel size you, however, want to have a careful look at. So you want to choose the pixel size just slightly below the Nyquist limit. And again, I refer to my lecture from 2 months ago. For a high numerical aperture objective, this typically means your pixel size should be of the order of 70 to 100 nanometers. For a medium range numerical aperture objective, the pixel size is probably more of the 200 nanometer range. You also need to set the Z-step size in the 3D stack to the Nyquist limit. And here are the values that I would recommend for the typical objectives there. Then when choosing the scan speed of your scanner, I would recommend choosing a high scan speed rather than a low scan speed. And if the signal is not good enough for that, then choose line averaging on top. So you get the same image acquisition time if you choose a 1000 Hertz scan speed with 10-fold line averaging, then you get with a 100 Hertz slow scan speed. But the bleaching and phototoxicity will be a little bit lower here if you choose higher scan speeds with line averaging, because the light is distributed over longer time. It's not hitting your sample once at a very long time, but multiple times for short periods. Line averaging produces less motion artifacts than frame averaging. I already mentioned that, so I would recommend choosing that if you can. And then a sequential scanning is the method of choice if you want to image multiple colors and you want to minimize crosstalk, and if you can afford it from a time perspective. It will be slower if you do image one color channel after another, but you will get higher quality images often. And here, if you can choose a line sequential imaging mode, that's also better than frame sequential imaging. Okay, with that, I want to thank you for listening, staying with me. I again went over time. And if there are any questions, I would be more than happy to answer them to you.
Okay, thank you so much. Yeah, pipe in if you have questions. This lecture series is really to give you those basic pieces of information in using your facility, but this gives you a chance to talk to Dr. Bewersdorf about maybe potentially your project that you want to do and what you should be doing as best practices for your imaging. How, for example, he's from the Yale Center of Excellence in Hematology, how they can help you or assist you in any way in this kind of thing. So feel free to unmute yourself and show your video if you have questions to ask.
So I put a whole hour aside, so we can ask, you can ask as many questions as you like. And Diane, do you want to turn off the recording?
Yes, I can at this point.